Hi and welcome back to maths class. Today we're going to be looking at limits and trying to understand a little bit more about limits in preparation for understanding more about when a function is or is not differentiable. That's what we're heading towards. So for now we're just looking at limits and reviewing what we already know about limits, and I'm going to start with this function here, which is f of x equals x squared minus 1 over x squared minus 1, where of course x cannot equal 1 because that will give us a 0 denominator. So this function is not defined when x equals 1. Now I know that the numerator of this function is a difference of two squares. X squared minus 1 can be rewritten as x plus 1 times x minus 1. Still over x minus 1, we can cancel out the factor of x minus 1 and we're left with x plus 1. But because of the way the function was originally defined, I still need to make sure that I note that this function does not exist when x equals 1. So what I end up with is a function that looks like this. It's a straight line. It's the line f of x equals x plus 1, but it has a hole in it. It has a gap at the point 1, 2, where x equals 1 and y would equal 2. There is a hole in this function, okay? There's nothing there. But although this hole looks quite big and fat on my diagram, in fact, it would be invisible. And no matter how far I zoom in and zoom in and zoom into this line, I get closer and closer, this hole has no width. It is exactly the point where x equals 1. But anything slightly to the left and the function still exists. Anything slightly to the right and the function still exists. So, a couple of key points here. Firstly, f of x is not defined when x equals 1. However, I can find the limit as x approaches 1 of f of x, and it's 2. And I'm going to show you how that works, and I'm going to emphasize a couple of key things about limits when we do that. So, what I'm doing now is I'm looking at the same function. F of x equals x squared minus 1 over x minus 1. And I'm going to explore numerically what happens as I approach x equals 1 from the left and from the right. Now, I've moved my values. I've started with a value of x to the left of 1, and I've gotten closer and closer and closer and closer and closer until I'm really getting very close to x equals 1, but still not equaling x equals 1. And down here, I've started with x is 2 to the right of x equals 1, and I've moved to the left bit by bit. I'm getting closer and closer to 1. Now let's look at what happens to f of x. From the left, I start with f of x equals 1 when x is 0. When x is 0.5, I've got 1.5. As I get closer and closer to x equals 1, my value for f of x gets very, very close to 2. And when I go from the right-hand side, the same thing happens. I start with f of x equals 3, but as my value of x moves closer to 1, my value of f of x moves closer to 2. Now, because of the function we started with, you would probably expect that to happen because, in fact, everything on this line is going to exist except where x equals 1. So just to the left and just to the right, I'm still going to follow the pattern of this straight line, which means as I get very close to x equals 1 from the left, f of x is going to get close to 2, and also from the right, f of x is going to get close to 2. Now, the fact that I can see that happening on the graph is another way of exploring this idea. But the key idea here is that I have approached from the left, I have approached from the right, and I'm getting very close to the same number each time. So, here is some new notation that you haven't seen. This negative here means from the left, so slightly less than 1. So the limit as x approaches 1 from the left of f of x equals 2, and I've explored that numerically. As I approach x equals 1 from the left, then f of x approaches 2. And this notation means from the right. The plus means my values are coming from the right-hand side from a positive direction. x approaches 1 from the right of f of x, the limit is 2. I got the same answer each time. Therefore, the limit as x approaches 1 of f of x equals 2. So in other words, I have found the limit and it does exist. Now, in order to properly understand that, let's explore an example where the limit will not exist. So what I've got here is a hyperbola. We know the function for a hyperbola is f of x equals 1 on x. Because I've got an x denominator, we know that that gives me an asymptote at x equals 0. When x equals 0, this function does not exist. So I'm not going to look at numbers. I'm just going to observe the graph. Sorry, see if I can get that all to fit. There it goes. By observing the graph, when x approaches 0 from the left, what is the limit of f of x? So let's get closer and closer. As I move x closer and closer to 0 from the left, what's happening to y? It's getting very, 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 very negative. And this is going to keep going towards infinity. So in fact, the limit as x approaches 0 from the left is negative infinity. What about from the right? The limit as x approaches 0 from the right, that's here. So let's approach 0. X is getting closer and closer and closer to 0, but this time from the right. Well, in this case, my graph is going up towards positive infinity. So as x approaches 0, y approaches positive infinity. Now, the left limit does not equal the right limit. I'm not getting the same answer as I approach from the left or right. And that means that the limit does not exist. So in fact, for a limit to exist, I need the limit from the left to equal the limit from the right. So to summarize, the limit as x approaches a of f of x exists if the limit as x approaches a from the left of f of x is equal to the limit as x approaches a from the right of f of x. Then we know that the limit exists.